Okay, for Algebra 9.7, this is our last lesson of Unit 9, and it is actually kind of a review because we've definitely already done linear. We did lots of linear earlier in the year. We did some exponential, not as much, not very much. We didn't talk about this a lot, but we did it already earlier in the year, and now our current Unit 9 is actually all about quadratics. So now this 9.7 lesson is just taking all three of what we've learned now and kind of comparing them. So let's take a look at each of the functions on a graph. So on a graph, a linear function is a straight line, and a quadratic function is a parabola. That's, remember, a symmetrical kind of U shape, or it could be upside down. And then exponential was like where it comes really close to the x-axis. It starts off really barely moving, and then it just shoots up really, exponentially quickly. Or it could also decay at a quick speed and then kind of level off. So let's look at the equations. A linear equation is y equals mx plus b. M is the slope. That's how steep the line is, and b is where it crosses the y-axis. Quadratic functions equation is y equals ax squared plus bx plus c. And remember, the c is the y-intercept. In order to find this lowest point, this minimum, you would do opposite b over 2a. That's going to help you find the axis of symmetry, and then you would plug it back in for these x's to find the vertex. And then you would pick a couple of points to reflect over to see exactly where a parabola is. And then a quick review of exponential. On a graph, it's a curved line. We already kind of talked about that, but the equation is y equals a times b to the power of x. X is going to stay x, but the b, remember, is kind of whatever the pattern is. How quickly is it growing exponentially? Is it doubling every time? If it was doubling every time, then this b would be a 2. And the a is the y-intercept, so it's where it crosses the y-axis. So a lot of times it just looks like 2x because maybe the a was 1. So 1 times anything would just be this. So sometimes it might look like y equals 2 to the x power, and that just means that your a term was 1, so it crosses at 1. Okay, so we're going to do some graphing. So we're going to choose which of these three models we're representing with these coordinates. So there's a graph right there. Let's go ahead and graph it. So put a dot at 1, 3. That would be here. A dot at 0, 0. A dot at -3, 3. I can already kind of tell what this is doing, but let's double check. A dot at -1, -1. And then a dot at -2, 0. So I can tell that this is definitely a parabola, which would be a quadratic function. So this is going to be quadratic. All right, let's go on to b. So let's put a dot at 0 up 2, put a dot at -1 up 4, a dot at 1, 1, and a dot at 2, and then 0.5. So 2 up 0.5. So it looks to me like it took a really big jump from here to here, and then it's kind of starting to level off. So I believe this one is a soft curve that is going to represent an exponential graph. So an exponential function. All right, and then the last one, let's do C. A dot at -1, -2. A dot at 0, -1. 1, 0, 3, 2. So if you look, they're missing this dot, but it doesn't mean it's not there. They just didn't choose that for us to plot. So this is going to be a linear function. It is a straight line. It doesn't curve at all. So linear, it has a pattern of up 1 over 1, so that's the slope, and it hits the y-intercept at -1. So technically it would be y equals 1x, so just y equals x minus 1. But it didn't ask us to write the equation. It just said which model. So we've got quadratic, exponential, linear. All right, let's look down here at problem 2. It says choosing a model for our using our differences or ratios. So which type of function best models this data? So here's what I want you to see. On the x-axis, it's just adding 1 every time. But on the y-axis, it's subtracting 4, subtracting 4, subtracting 4, subtracting 4. So this is a pattern that is linear. The first distance, oh, it says right here, the first distances are constant. So it is, if it is constant, it is linear. If it is -4 every time, and you don't really care about the plus ones because they're just choosing which axis to choose, and they just chose one apart from each other. So those don't really matter as much. We're really looking at what's happening on the y-axis. So it's constant. They're subtracting 4 every time. So this one is linear. Okay, on our B graph, the x's are, once again, they're choosing ones that are right in a row, and that's just smart. We usually choose x's like that too. But once they have plugged it in, they have 0, -0.25, -1, -2.25, and then -4. So here's what's happening. From each one of these, first it's subtracting 0.25, then subtracting 0.75, then subtracting 1.25, then subtracting 1.75. And if you look at the difference one more layer out, each of those are subtracting an additional 0.5. So that is not continuing to go up at an exponential amount. It's just going up at a constant but second tier amount. So this would represent a quadratic function because not the first differences are constant, but the second distance differences are constant. So that would be quadratic. Okay. Let's take a look at this. This is not in a table, but it is in an ordered pair. So we can go ahead and put it in a table just because that's how our A and B examples were. So if we did -1, 0.5, 0, 1, all I'm doing is writing these into our table. 1, 2, 2, 4, and then 3, 8. So what I'm noticing is, of course, these are just going up by ones, so I'm not actually even looking at the x's. I'm really looking at the y's. This one goes up 0.5, and then it jumps up 1 whole, and then it jumps up 2 whole, and then it jumps up 4 whole. So what's happening if I go another layer out, it's jumping up 0.5, 1, 2. It is doubling each time. My first tier is not constant, nor is my second tier. And I know it's constant as far as it's doubling each time, but it's not constant as far as the exact same amount that is being added or subtracted each time. So if it is doubling or tripling or quadrupling or doing something with each tier that you go out, this is an example of an exponential graph. Exponential, there you go, function. Okay.